Okay, I think we're going. Sorry, let me get this straight here. Okay, hello everybody. Hello everybody, welcome back to another live stream from Deep Astronomy. Hopefully we're not going to have any problems this stream, but we always do, so we'll just get prepared for it, I suppose. My name's Tony Darnell. I run Deep Astronomy, and today we're going to be talking about habitability and exoplanets. There's kind of a problem with how we're talking about this, and I want to highlight it just a little bit in today's stream. But before I get started, let me let you know that I'm streaming on YouTube, Twitch, Twitter, and Facebook, as well as I think Odyssey, and I think I'm going to add in LinkedIn probably next time. So welcome. If you would like to interact, I'm seeing all the chats from all those platforms. But an even better way is if you go to the Discord server. There's a link in the description box at YouTube, and I think also in Twitch, and join that server. We will very quickly get you permissions to be able to interact and join in. I just found out, or at least I just remembered, that if you join the Discord server, because of problems with bots and all that kind of stuff, there's an extra step that we have to give you manually to give you permissions to post on the server, and we give you a role called Can Participate once you've joined the server, so you can't just automatically jump in to the live stream. It's sort of a protection against a lot of the stuff that goes on in Discord. So hopefully the mods, if you're a mod on Discord, I'd appreciate your help. Please go to the chat here first channel and approve people who have joined via the link so that they can jump right in, give them a Can Participate role. And let's just assume they're not bots, because they probably won't be if they're watching this. Bots don't tend to watch my live streams, as far as I know. Okay, I got to show you something, guys. This is happening right here, right now. This is a screenshot of the radar of the area, and I'm seeing incredibly dark skies right now. Tornado warnings are in effect, and I hope, beyond all hope, this won't be a problem. Panther is right here at my feet, shivering like crazy, lots of lightning and thunder. So if something happens in the stream, you now know why. This line of thunderstorms, this was taken about an hour ago. These have now gotten a lot closer. And so that's going on right now. As with all things, everything happens at 3 o'clock on Thursday. Getting a little tired of this, but anyway, that's how it goes. So I want to let you know that that's happening. So just to be, so far it looks like my internet connection's fine, and but if I do drop out, that's why. Okay, so I'm looking at everybody's. I'm looking at the live chat just to make sure it all works. I can also do this. Mark Zuckerberg has announced a new name of Facebook, Meta. Is that true? Is that really true? Oh man. Okay. Well, Facebook. Oh, what a mess. Okay. I wanted to show you something. I wonder if I could pull this up. Let's see. Well, I meant to have this queued up before I started, but I got so busy getting ready for this stream today that I didn't do it. I just read, I think it was on Gizmodo, maybe it was in Gadget, that NASA is really confident that the JWST is going to launch on December 18th. They made some comments today to some reporters that indicated that because the way things are going down there after the last launch of the Ariane 5 rocket, they're feeling like they're going to make the December 18th launch date. They're very confident about this. Apparently, also the JWST spacecraft has passed a lot of the pre filling up with fuel checks. So I wanted to have that queued up, but I just didn't have time. So that I just read today. So JWST is going nicely, and that's good because we're going to need it, especially when we talk with some of the stuff that we talk about here today. So I wanted to let you guys know that. Hello, Dr. Lungworm. It's good to see you on Twitch. Dennis is also on Twitch. All you guys. Susan H. is also no, you're on YouTube. So welcome. It's good to see you, Susan. I'm glad you're here. And of course, John, my friend from UK. Oh, that's disillusioned. It moved when I clicked on it. John Suffel, my friend from the UK, is also here, and I think Adam is probably lurking somewhere around as well. Anyway, welcome, guys. It's good to see you. We get together twice a week. Another little bit of news. Got off the phone with Dustin Gibson from OPT just before I started streaming, and we are definitely for sure starting up Space Junk Podcast probably in November with a lot of other products that are going to go along with it. We'll have a blog post. I'll make some small videos out of our stream. We're also going to live stream the recording. Probably is on Fridays, so if you guys can make the live recordings when we stream them, probably on Twitch, but also probably on Deep Astronomy as well. We can interact with you, and if I see a question or comment that you guys asked during this, then I can incorporate it into the podcast straight away. So that's coming up as well. Also in the can is the first Space Fan News in a long time. That's coming out Sunday afternoon, so you can look forward to, or you can look for that as well. Yeah, I don't want to talk about where you guys are from, but since you brought it up, he's from Lincolnshire. Okay, I don't like to point out your geographical locations just in case you're nervous about that, but I do say UK is big enough that it's probably safe to say that. I'm not gonna say where you're from, John, so I'll leave that to you as well. Okay, so here we go. Let me pull up my stunt. By the way, if you are watching on Discord, you're only looking at my screen, not this camera here. Just too much bandwidth to go through right now, so you're just looking at my screen share. But after I get done with these slides, I'm going to put my headphones back on, and if you're in the live stream chat voice channel, then I'll hear you, and we can start. And I'll put you on the stream and make sure you're not on the stream now, because that would be annoying and I wouldn't hear you because I don't have the earphones on. I'm also not going to look at the live stream, the chat, because that's distracting while I'm doing it. So I'm just going to, so I'll be able to get through this stuff. Okay. The need for an exoplanet habitability index. What do we mean by that? Well, let me point you to another resource. If you don't know about astrobites.org, you need to learn about this stream. It was inspired by this post. Astrobites.org does a lot of things that we did on T Cubed for many, many weeks over the summer. It picks a paper or a group of or a set of papers, and it writes about them in an easily understandable format for the general public. And it is designed to help early career scientists and grad students and postdocs a place to hone their science writing skills. So they take a paper and they basically translate it for the general public. And this one is inspired by an article that was written by Ali Crisp, and she's a fourth-year grad student at Louisiana State. She wrote this article that I'm using as a guide to talk about for today's live stream. This is a great resource for you because I know why you're here. You guys are here watching this stream because you want to learn about the latest things in science. And this is one of the sources I go to. So that's the first thing I wanted to let you know about. This is the second one. If you don't know about exoplanets.org, then go there and explore, because this is where I've gotten a lot of resource material that I'm going to use today. I went there today to make a series of plots on the data that they have. You can go do this too. It's a fun thing to do. And all of the data on all the exoplanets, both confirmed and unconfirmed, are there. So you can explore this. So here's a snapshot of their homepage. And you can see that we have a total of 3,262 confirmed planets. There's another almost 2,500 unconfirmed planets, for a total of about 5,747 exoplanets that we know about so far. And there are a lot more out there. Based on this data, based on the observations that have been taken so far from Kepler and TESS and ground-based telescopes, we can extrapolate on this and discover, or say, that there are about 1.5 planets for every single star in the Milky Way galaxy. That's a lot. Now, not every star has planets, but on average, there's 1.5 for every star. That's how many exoplanets we think there are. So I made some plots. I just went over there and I did this in like, I don't know, 2 minutes. I picked a thing and it produced this plot. And I wanted to know about planetary radius. And I only used the ones that are confirmed. I excluded the candidates in these plots. So these are only the 3,262 confirmed planets. And here's what they look like so far. This is their planet. This is a plot of their planetary radii. Most of them are a little bit larger than twice the size of the Earth, but there's another bump here at about 10 times or maybe 11 times the orbit of the radius of the Earth. And there's a bump there. These are these Neptune-sized planets that seem to be proliferating in the distribution here. But there's some biases in this, which I'll talk about in a minute. Here's the orbital period of all those planets. Most of them, this is one of the biases I was telling you about. Most of them orbit their stars around 10 days, sometimes 100, up to about maybe 100 days. Now, the reason that the results are skewed this way is because of the way in which we have found these. Most of these were found with Kepler by staring at the constellation Cygnus for 5 years, and it's built up this orbital picture of how many times a star or the planet orbits its star. That's its year, and most of them are short because that's what we tend to look at when we see light curves. We tend to see the most light curves, and we can confirm more of these planets the more observations we have. Every time a planet moves in front of its star, we get a detection, and we can infer from that its orbital period, and that is outlined here. So we have a bias towards short period exoplanets, but that doesn't mean that's all there are. That's just what our current observing techniques are biased towards. But this is the distribution so far. I expect with more long-term surveys, these numbers out here we'd see a lot more longer ones. On the Earth, as we know, it's 365 days, so it'd be in this region here. Oops. Here's their masses. Most of the planets we know so far are about this massive, about roughly 5 or so Earth masses. Again, a peak towards the Neptune-sized. Here's their separation, their distance from their star. Most of them are very, very close to their star, and this makes sense for the bias I just told you about. Short period exoplanets tend to orbit their star very quickly in a matter of days, which means they're probably pretty close to the star itself. In this case, about 1/10 of an astronomical unit. And from a lot of these observables, their size, their distance from the star, their orbital period, all these things, we can get a sense of. We can infer from that things like their density and properties like that, from which we can infer their surface gravity. And most of the gravity that we've seen, most of them have a surface gravity around between 3 and 4, that of the Earth. G's, I guess, is the thing. That's the separation. I'm going the wrong way. So the things that we can learn about exoplanets right now, the things we've been learning about so far, we can get their size, we can get their masses, we can get their orbital periods, we can get the distance from the star, and we can tell the number of planets in the system. And from those observables, we can derive things like its density and its gravity of that exoplanet. And we can infer this thing called a habitable zone, and we can infer that from this distance from the star as well as the star type. A very small red dwarf would have a habitable zone much closer to it than, say, a red giant or a blue giant star. They all have distant relations to the star itself in terms of whether we call them habitable. Now, I just want to very briefly talk about the methods of observation. These are the 3 ways which we find exoplanets. And this plot here on the right, this is an example of microlensing. I was putting this together really quickly before the stream because I realized I forgot this slide. And so I needed to talk about how we find exoplanets. Whenever a star with a planet in it passes between us and a distant background star, the gravity from the lens from the star with exoplanets actually increases the brightness of the star behind it. And here's a curve of that right here. So here's us. There's a background star. Here is the star, the star with planets in it. And when it passes in between, it makes the background star brighter in this fashion. However, if there is a planet in orbit or more planets in orbit around that star, then when it passes in front, it makes a characteristic brightness blip that looks like this with time. And that's how we can find exoplanets. And based on the size of that blip and its frequent and its uh, uh, I guess where it is along on the curve here, you can also see how many planets there are as it passes through. So that's the microlensing technique. But I wanted to really quickly show you the radial velocity method. I have to. Sorry, this is kind of kludgy, but I'm sorry. I'm going to show you the transit method first. So here's the transit method. When a star passes in front of us, and our planet passes between us and the star, it dims it out like that. Okay, the duration tells us a lot about its orbital speed. We can learn a lot. These are all the things we can learn about the star as it, or the planet as it passes in between us and the star itself. This is a really good animation. It shows this quite nicely. So this is one way in which we find it. Thank you, Hans. I see you. Thanks, man. Okay, so there's the transit method. And let me show you the radial velocity. Where did it go? Here it is. This one's from ESO. When a planet is in orbit around its star, the gravity of that planet tugs and makes the star wobble. Our sun does this with all the planets in our solar system. It wobbles in that circle like you see in the star in the center. And as it goes back and forth, the spectrum of that star moves back and forth. Those are absorption lines in the spectrum of that star, and you can watch that. That is an indicator of the wobble. The direction of the movement is whether the star is moving towards us or away from us. And so we can get a sense from this, the mass of the star or the mass of the planet, how many planets there are, as well as its distance from the star. That's the kind of things that we can learn from this. So that's radial velocity. And right now, those are the ways in which we can observe exoplanets. Those are the three main ways that we find them. Kepler used the transit method. Ground-based telescopes tend to use the radial velocity method because they don't require as much of a higher photometry sensitivity. And those spectra are better to take from the ground than from space because, again, the atmosphere screws around quite a bit with the photometry, enough so that it's hard to do the transit method. It can be done, but not as accurately as in space. So that leads us, so that's very brief, very quick rundown on all the planets we know about and how we find them, because I wanted to set that stage to get to this. The infamous habitable zone. We hear about it all the time. And right now, it just means this. That means that the star and the planet geometry is such that if the water is on the planet, then it can be liquid. Now, that if water, is on the planet. So there you go. That's how quickly I was putting this together prior to the stream. That's all it is. That's it. That's all we mean by the habitable zone. If, I mean, it's a little bit crazy if you think about it. If the planet that we see is in an orbit that is around a star, and it is a distance from that star such that if that planet had water, then it would be liquid if it did. And we're saying that's a habitable planet. Well, that is way too incomplete. We need to do much, much better than that. So, and you've heard me make fun of this all the time about how we're calling things planets. Now, one of the things that's habitable planets. And one of the things that's interesting about the way we observe these things is that from the observable things that we can get, radius, distance, mass, uh, uh, um, orbital frequency, all that kind of stuff, orbital period, all of that stuff that we can get from those observables, we can deduce things, like I said, about how much gravity it might have, whether it's a very dense thing or not. But we have no way, zero way, of finding out if there is an atmosphere on that planet yet. And that's where, again, I've said this before, but I'll say it again, JWST is going to be leading the way on this because it's got near spec, which we talked about last time, and it near spec will block out the light from the star so that we can get the spectrum of the planet and see if it does in fact have an atmosphere. And if it does have an atmosphere, then what is it made of? We need to do way more. But right now, I think, my opinion, and I think a lot of people agree with me, that exoplanet researchers, especially astrobiologists, take this, they get a little bit ahead of themselves here. We say we think this could be a water world. We see headlines all the time. This could be a water world. This could have life. This is an Earth-like planet. When really all we know are the things that I've outlined. We're really kind of overstepping what we can say about these exoplanets. So in order to rein this back in a little bit, we need to and this is what the authors of the paper, by the way, the link to the AstroBites is in the description, plus the link to the paper, which is open access. So you can read this paper that we're talking about now too. But they're arguing that we need to increase our what we're calling a habitable planet. And the reason, and a good idea is to start with what ecologists do here on Earth. Okay. And I know that you guys are going, why are we also, hell bent on comparing everything to Earth? Why does it always have to be Earth like? Why does it always have to be like the Earth? Well, because that's the only thing that we know of that's habitable right now. So, how common is that use case? It makes perfect sense to ask the question, how many planets like the Earth are there out there? And why don't we, when we look for a habitable exoplanet, why don't we at least start with what we know, which is here on Earth? We already say liquid water is important. In fact, that's all we're saying right now when we call something habitable. But we start with Earth because we have a lot of information here. And what can we learn about other planets based on this? So, and the reason that's important is because even here on Earth, a very habitable planet, at least right now, it's getting less so as time goes on. But even here, right now, not all places on Earth are equally habitable to all the species here. And a little bullet point given in the paper is you won't find whales in the Sahara Desert, right? So it matters where on the Earth you are as far as what species you are and what might actually live there. And so even within a planet itself, having liquid water is not enough. You want to be able to look at that and tell the zones if there's any habitability zones in there. So we need to account for a lot of things, like the composition of the atmosphere, what's it made of, and what's the whole planet's global conditions like. And of course, we're going to find that there's going to be a range of habitability. Not all planets are going to be all the way habitable for everything, even here on Earth. So I think it's a good way to start. A good place to start is by this. And so the geologists, as I said, have been working on this problem on Earth for a long time, and they have well-established models for the habitability of here, of different terrestrial environments here. And they call them habitat suitability models. And like we would look at, say, the Amazon basin, that would have one sort of model, and it would give a way of finding out how habitable that is for different species, right? You could easily say, well, in the Amazon, it's probably not going to be all that habitable to, say, a Gila monster or something. Maybe it is, but I'm just coming up with this on top of my head. And using the other example, you do a habitability model on the desert regions, and you're probably not going to find a lot of dolphins there, right, living there because of the specific conditions in that region. So you need to consider all those factors, the temperature, how many nutrients there are, as well as disturbances to the environment. This is what ecologists do now here on Earth. And all of this leads to an index, a habitat suitability index for different habitats. Now, this was in the paper. I took this from Ali's post, and I'm going to be honest, I don't fully understand it, but this is an example of a model, a suitability model that ecologists run. So in this one case, they make a grid like this for rainfall, and they make another one for altitude, and then they look at what they've observed, and they can put those together to put a model that based on rainfall and altitude, then these are the habitable regions. In that, this might be a topographical map, where these regions would be habitable. And so the granularity here can be as high as you want. The model can, well, I think it's probably going to be limited by the model, but this is an example of a habitat suitability model. So what should we do? How do we apply this to exoplanets? Well, an HSM habitat suitability model can only be validated for other planetary environments if they happen to be like the Earth. So again, we're comparing things with the Earth, and this is a challenge, right? And these models need to include all the stuff: temperature, nutrient concentrations, any precipitation, what areas are comparable with Earth. We need to ask these questions about the exoplanets themselves, and what are the limiting factors. Right now, our observations are only telling us a very small amount of things we need to know. And so what and finally, what information suggests habitability? What do we know from our observations that would say to you that this is a habitable place for life to be? And then establish some kind of scale and threshold for habitability. You want to know things like how much biomass there are. And when you look at the places where we're going to start, obviously, is going to be with biosignatures in the atmosphere. Things like methane concentrations. Are they like here on Earth? There's several kinds of methane, and only one kind is produced from organic life. So we'd want to be looking for that. And all of this stuff together combined, we could then apply an index to that exoplanet to say how habitable it may or may not be. And so just today, I mean, this was a freaky thing. This passed my news feed today. Even NASA is calling for this. This is from phys.org. I saw it was posted today, and NASA is calling for a methodical approach to identifying life beyond Earth. And so let me pull up that. I pulled this post up. Here it is. So here's the post on the website, and there's it says they would have what this would consist of is a several level system that would tell people, whether or not we have found life on another planet. This is a systematic approach to not only applying a habitability index, but also categorizing whether life exists on that exoplanet. And so they're calling it the cold scale, which is the confidence of life detection scale. And it would consist of several levels. The first level would be assigned if detection of a biosphere suggested life might have been found. And this would kick off a second level, which would involve ruling out other factors such as contamination. Make sure your observations are good. And then once that passes, a third level would begin that involved making predictions on how such a signal could have generated. If non-biological sources are ruled out, that would move the effort to level 4, where observation of the signal would be verified via other means, pushing the effort to level 5. And if such means are found, then the signal can be moved to level 6, which indicates that the signal is deemed related to a life form living beyond Earth. And the final 7th level would involve follow-up study of the life form. Finally, we've got they're thinking about, well, why don't we approach this in a more systematic way? How are we going to determine if there is any kind of life on these planets or not? And this is this scale. I mean, this is amazing. It just came by my feed just today. But it goes on. This article goes on to state that if such a scale were to be used by the science community, it is notable that some events would already meet the conditions of the first level, the detection of methane by ground-based telescopes. Some have already found this. It could be argued that NASA has already taken steps to move the detection of methane to level 2 by sending spacecraft to Mars to measure surface levels. And sending a flying craft that could measure different levels at different points on the surface and identify the types of methane being emitted might take the effort to level 3. So that's an example of how you might apply that system. So I don't know. I mean, I think that's pretty cool. I mean, you know, this we need to get beyond this idea of just, well, it's in a habitable zone. A this might be a water world, whatever it is, just based on the few observations that we have so far. So let me just pull this. Okay, so that's my little spiel, my little presentation that I put together. I think this is important. I think we're getting too simplistic in our thinking about exoplanets and life in the universe, and we need to get way more analytical about this if we're going to be serious about deciding whether or not a planet is habitable or not. So this habitability index would go very far, I think, in doing this. Now, what's the biggest problem? Well, okay, yes, we could make the assumption that the planet, whatever it is like Earth. And once we've made that determination, then we can go through all these ecology models and apply them to whether or not to a region or a planet itself is sustainable as far as its habitat goes. But we need a hell of a lot better observations than we've got right now. And some of the ground-based telescopes are taking spectra of atmospheres. I'm going to be honest with you here and say I think the error bars on those are probably pretty high just because of the light from the background star, the host star. But so we need better observations from things like JWST, or at least ground-based telescopes that have chronographs on them to block out the light from the star, which I think they are making progress on. But that's a first step. That's just we need to know, is there an atmosphere? We need to get at least that far. And then we can ask the question, yes, there's an atmosphere because we can see it in the spectra, and here's what's in it. That's the second thing we want to know. And I'm sorry, but with things like JWST, that's about as far as we're going to go. We're going to need a hell of a lot better stuff to get more information. And I talked about Exo Life Finder all the time, but that telescope I think is going to be vital. It's a special purpose telescope designed to do just this one thing, and that's find life elsewhere. And they've got a design that will work on this from the ground that I think needs to be commissioned. So the Planets Foundation has done some great work on this, and I have nothing but hope that will translate into an actual telescope at some point in the future. Okay, so I'm seeing that Nick Holland on Discord has already made a comment. Is it possible? Hang on, my thing is in the way. There we go. Oh man, sorry. Discord got in my way. Hi Tony, is it possible to confirm an exoplanet transit with amateur equipment? I'm currently running a sequence to get transit data for Kepler 42b. Not sure it's going to work because it's at mag 16, which is very faint, and I only have an 8-inch SCT. Hope it works. The answer to your question is yes. And the person you need to get in contact with is a fellow by the name of Mike Akey. He's on Twitch. He's also in my Discord server at some point. He runs a very large plane wave telescope where he is actually in the process of confirming test candidates by getting further observations in. I can't speak to, I think a C8 might be, or 8-inch, you might have a Meade. That's pushing it. On mag 16, you need to be able to have very precise photometry, and Mike can help you with the standards that the professionals are using to validate. You can definitely do this, but you've got to meet certain standards, and they want to see how you take your data and calibrate it. And then once you get those put through to them, then they can let you in their system. Or if you don't care about any of that, you can just do it anyway and make your own light curves. It is possible. And there are resources out there. Mike Akey is one. Another one is Mike Forsland. He's known as Asteroid Hunters on Twitch. And he also has a YouTube channel here. He live streams his stuff. Now, he verifies asteroids primarily, and he puts them into the Atlas database. But he also does exoplanet work with Mike. So the two of them have a lot of resources and could help you, point you in the right direction, because they do this all the time. Amateurs, this is the future of the hobby, in my opinion. I think this is where the hobby of amateur astronomy is going, is by doing this kind of work. Confirming exoplanets that already exist is one of the areas that I think is most exciting. Also near-Earth objects and all that other kind of stuff. So the answer to your question is yes, and those are the best resources I know of. Asteroid Hunters on Twitch, Mike Aitke, AITKE, on Twitch also, and he streams, but I don't know if he streams as much. So so reach out to them, or maybe do it via Deep Astronomy Discord server. They might know. So anyway, it's a good question, Nick. Okay, so here we go. James Dugan's got some. Jimmy D down in Australia. Should oxygen be added to the criteria? Of course. Or is that biased to Earth oxygen consuming life? Yeah, absolutely. You need to have oxygen in there. I don't see anything wrong with using Earth analog comparisons. I mean, one of the questions we want to know the answer to is life common in the universe? And are we common in the universe? Is Earth common in the universe? That's a huge question. The conditions that happened here allowed life to spring forth, but how common is that? We have no idea. We have no idea that what happened here has happened elsewhere, or even if it's common or not. So I don't see anything wrong with trying to compare things with Earth. Yes, maybe you limit things a little bit much. Maybe we would, but you got to start somewhere. And I think it's very, if you're going to pin down life in the universe, you need to start with the one place we know what happened. Now, my feeling is that life in the universe, I waffle on this. Right now, I'm kind of thinking it's not so easy, but I'm thinking that, some life is common, things like bacteria or maybe even, complex animals like mammals and stuff. Maybe stuff like that can eventually, thrive in an environment. But, you know, uh, I don't know how. I mean, I go back and forth. That's easy. It's hard. I don't know. We just don't know. It's just a feeling. It's a very non-scientific statement for me to say, I think life is hard because, I don't know. There's no data points anywhere else. And it's even worse when it comes to talking about intelligence. So forget that for a minute. Let's just focus on whether life is possible or common. And it seems to have happened relatively quickly after Earth formed. But again, it's not that quickly. 3 billion years, 2 billion years into it, it finally comes around. That's not that quick. So I don't know. I don't know how common it is, but we do need to do, I think, Earth-related observations. Now, you could say, well, Earth didn't have a lot of oxygen early on when life first started out. The plants and things that followed brought the oxygen to the Earth, and that's a good argument. So you don't want to exclude oxygen, but you definitely don't want to exclude it. You want to leave it in there in your observations. So you definitely want to include it, I think. Fish head salad. That's an interesting moniker. Wouldn't it be interesting if Mars and Venus were still Earth-like? They have water, cores, magnetic fields, rotations, etc. I still think about that all the time, except that they're not Earth-like. Mars is very much smaller than Earth, much smaller surface gravity, no magnetic field. Venus has an atmosphere that can crush you. It's about the same size, but rotates the wrong way, and it's got greenhouse gas, the greenhouse effect, run amok. So it's not very habitable. They do rotate, though. You're right about that. And there is some water on Mars as well, but there's no core. There's no dynamo on Mars to speak of. I talked about that a lot during the terraforming hangout. So let's see. I'm scrolling up through the thing here. I'm hoping Planet 9 will be found. Yeah, they're still looking. There's Still looking. Thanks again, Hans, for the support. I appreciate this. This is very helpful. I do appreciate that. X flares a few hours ago from the sun. And Hans, still don't get why we search for anything but an exact copy. It's not exact, but we do want to. I think look stuff like ours. I don't know. I think it's worth doing. Okay, let me see if is anybody in. Oh yeah, a couple people. Okay, so I'll put on my earphones. Hello, Discord. I'm here, so if you want to say something, go right ahead. I can hear you. Oh, hold on. Okay, go ahead.
So you've got these orbits. Is there anything in that database about eccentricity? Like we have a pretty close to circular orbit here.
Yeah.
And I think that the eccentricity would also play a part into that, because if you have a wild eccentricity, then I mean that would affect your seasons or whatever.
Yeah.
And I don't. Is that in that database?
Mm-hmm. Yeah. So if you go here, and we want to make a histogram, we type in. These are all the things you can plot. The orbital parameters are in here. Orbital eccentricity is one of them. Let's make this a logarithmic plot. So there's the orbital eccentricity of all the planets discovered so far.
Cool.
Yeah. Yeah. So yeah, just spend some time on this. Let me get rid of this comment here. Yeah, so you can just yeah, and that's how easy it was to make this plot. I just
awesome.
And you can include let's see what else. You can include Kepler's data if you want to, Kepler's unconfirmed data if you want to. So that's all in here. And so yeah, it's that simple. And these are all the things you can plot against. One of the things I don't understand is a thing called, see if I can find it, impact parameter. I don't know what this is, but I've heard the term. I don't know what an impact parameter is, but I need to find that out. Anyway, that's something that I wanted to find out more about, is what that is. But these are all the things that if any of the planets were found by microlensing, they would show up here. Stellar, let's see, orbital elements. These are the things you can do about the orbital inclination. We can find out that semi-major axis, the planet mass. I did that plot for you. It's including Kepler data. I didn't include that in my plot. So yeah, man, just play with this. And this is on exoplanets.org. You see how easy it is. And this is dealing with all of the confirmed data and the candidates that that would work, that we currently know about. So it's definitely a good resource. So that with AstroBites, if you get nothing else from this stream, hopefully you will appreciate those two resources, because I know that my audience here is very into learning new things about the latest research, but they may not always have the understanding of the jargon or the background, and AstroBites breaks it down for you. So please go and support their work by just reading it, and maybe leaving comments if you want.
Yeah, the exchange of information, that's what you're doing. You're disseminating it there. That's great.
Yeah. Yeah. So let's see. There's been a lot of chat about an XClass flare. So let's see. Orbiting satellites have just detected an X1 class flare from Earth-facing sunspot AR 2887. The blast is at well, where are you getting this information from there, Spitfire? Let's pull it up. The blast is at 1535, October 28th, created a massive tsunami of plasma in the sun's atmosphere. This might be coming at us in a couple of days. The only resource I know of is space weather. Go spaceweather.com. And yep, there it is. So there it goes. There it is. There's your X-class flare. This is from SDO. Wow, look at the shockwave go across the disk. Oh, wait, you can't see it because I'm not sharing my screen. There we go. There it goes. So there's the animation. There's the XClass Flare right there. And you can see the shockwave. We might get a piece of this. It's down in this hemisphere, so it might be a little bit, or it's Earth directed, but not directly Earth directed. It's not coming straight at us. It'll be more oblique at an angle. That's a big flare. It's definitely a big flare. Oh, so you got this. You got this too, Spitfire. I see how you copy and pasted this. So yeah, okay. So I'm glad we use the same resource. Spaceweather.com, a third resource for you folks, and they send alerts out too. So you can definitely check this out. I wonder where the Parker Solar Probe is right now. Let's find out. NASA eyes. This is the fourth resource I'm telling you guys about. NASA eyes. This will tell you where all the probes are. NASA's eyes, eyes.nasa.gov. And if you hit on, there's different sections. Let's go on the solar system. Seems to be taking a while to load. There it goes. Welcome to the solar system. And you can see the solar system. And if we zoom in, hopefully you can see this okay. Let me zoom in. There it is. There's a Parker Solar Probe. Let me zoom this in a bit more. This is going to be faint. I don't know if you guys can see this or not, but Parker Solar Probe is right there. It's not making one of its close approaches to the sun, so it's probably safe right now. It's close to, well, kind of close to Venus. It's heading towards the sun now. But there's a picture of, this is really slow. It could be my connection. I don't know. But there's the Parker Solar Probe. And I'm just zooming out a little bit. So that's where it is in relation to the sun. And I don't know, let's see where Earth is. So if that's Earth directed, let's see if the Parker Solar Probe will get hit. Where's Earth? Where are you, Earth? Go away. Let me scooch way back. Come on, this is really slow. Look at the inner solar system. Let's see if that's faster. There we go. Okay, so here's Earth. Here's Parker Solar Probe. And if this flare is heading our way, it looks like it's going to miss it. So Parker Solar Probe looks free of this event. So see all these tools that are available to you? I just call them up in a second. You can do this too. There's stereo. There's where stereo is. And if we zoomed in on Earth, we could see where Tess was, and you can see where Kepler is, and all of this kind of stuff. Kepler's still up doing things, although I think it's lapping the Earth now in its orbit. But all this stuff, there's OSIRIS-REx. It's on its way back with that sample of Bennu. Okay, so flare coming our way. Better and Better's like, I check out space weather whenever the internet turns to shit. Yes. Okay. Jimmy D. We can always do bigger telescopes. With bigger telescopes, even NASA suffers from aperture fever, like all astronomers. Very true. Always need a bigger one. Oh, well, thank you, Dennis. I feel like I get distracted sometimes, though, and I don't make good points, but thank you very much. Yeah, you said took it from space weather. That's good. Well, we guessed correctly. So it's the only resource I knew of where if I wanted to get fast information on a flare, I'd just go there. Another one is, let me see if this is still up and running. I'm going to show you something that I used to work on many, many moons ago. mlso.hao.ucar. Does it still work? Oh, no, it's not there. Oh, I typed it in wrong. Let's see. mlso.hao. Oh, it's moved. There it is. There it is. Mauna Loa Solar Observatory. They operate all these different wavelengths from the mountain of Mauna Loa, and they are the only people that do this. This is the mark. Oh, it's called the K Coronagraph now. This is the only ground-based imager that can take a picture of the solar corona. And they used to be, I don't know what they have now, but this used to be a linear diode of about, I think it was 256 elements. It was a CCD of one row, and that one row would rotate around the solar limb once every 3 minutes and scan a photo or scan the K corona. This is the uh, very inner corona. This dotted line, that's the limb of the sun, and the outer corona is right there. This is the only place you're going to see this that's not in space. The other one is the better coronagraphs are up in space on the SOHO spacecraft, the LASCO ones. Here's a CME from earlier this year. They do a subtraction so you can see the waves of the thing itself. They also look at the comp instrument. I helped work on this, and this measures the solar corona magnetic field, or the magnetic field of the sun, I should say, by looking at polarized light from the corona. It measures this using liquid crystal variable retarders, and I helped with that instrument many, many years ago. 2005, I think I worked on that. And then there's H alpha, which many of you can do now with off-the-shelf telescopes, but I don't know what resolution or what wavelength these are. But if you access all data, this comes up. This was my idea. This calendar, I built the very first one way back in the early 2000s, and it was based on the Unix cal command. If you type in cal on a Unix command line, you get the year's calendar. And this was based. Now I'm sure it's a hell of a lot more. But the color coding is X's mean they don't have data. They have all data sets if it's green. They just have some of them if it's another color, and then of course if it's blue, there's a CME to look at in that data. So they've flagged it for whether or not you can see a coronal mass ejection. So that's another one. That's another place, and the real value here is both comp. For it won't be that big a deal for you because you don't care about the magnetic field strength. But this is cool. This, getting these latest images of the solar corona from the ground is great, because the LASCO C2 coronagraph, which is in space, it's somewhere way out here. Okay, so you can't. In fact, I wonder if that dotted line doesn't mean that's where that's where C2 starts. Anyway, it's a region of the solar corona that isn't visible from space because they can't get down this low. So there you go. Another resource. All this free stuff that I've just shown you about. You should have a lot of fun with that. mlso.hao.ucar.edu. Old friends. Is what 1 hour old? Hey, Pyro, it's good to see you, by the way. I'm glad you're here. Julia Enriquez. How's astrobiology coming along with in the metallicity department? Technically, only complex chemistry can evolve life as we know it. After all, how would this factor into the index? That's a great question. Um, I think it would have to factor in, right? You don't a low metallicity star, and by that they just mean one with hydrogen and helium, would probably be in. Well, there aren't many of them around. I don't know what the distribution of that is, to be honest. I better not say, but it would definitely matter, wouldn't it? If one would think that a planet that had life on it would come from a debris disk or a protoplanetary disk that orbited a star that had lots of elements in it already. These are the elements that have been generated through previous generations of star explosions, so that you can get these heavier elements, things like carbon and oxygen and all of the other things that go into building a planet. Iron, all of these things matter. Gold, for example, comes from multiple neutron star collisions, right? So these kinds of things you would need an older, or I should say a newer generation star, one that has been formed relatively quickly, recently in the universe, rather than these poor metallicity ones. So I would say to you that that would be a good addition to any index that we give a habitability factor to of an exoplanet. Is the star around a high metal, or is the planet around a high metal star? I think that is a good question to ask. Very good, Julia. I like that a lot. I'll forward that on to people. Nobody listens to me. Can't wait for TRAPPIST-1 system on JWST. Very true. You know what? Watch Space Fan News on Sunday when I post Space Fan News, because it's about JWST doing something cool with regard to stuff. I don't want to tell you because I just made the thing on it. So let's see. I think I've read everything, and I'm running out of time anyway. Oh, Abdul, are you serious? Yes, I do have a Discord or something. The link's in the description box, man. Go down there, click on it, and then one of us, Ahmad, is going to have to give you participate permissions, because like I said at the top of the stream, you can't just jump in and start making posts, because we had Uncle Bill and Better are people who really have helped this Discord server become great. And we had to put up a firewall to keep bots from just spamming us to death. So we require a human to verify that you exist. So you go in there, you sign up for the server via that invite that's in there. You'll be sent to the chat here first. Leave some kind of chat. Say something, or just wave. And then somebody will give you the can participate permission. And then after a few permissions or a few interactions, that if we see that, you're not going to be like a troll, then one of us will give you a space fan role. And that is where you can do virtually anything. You'll still be able to get into the live stream. You still be able to do anything, actually. But, you get a slightly better role once you've been there a little bit. So that's the way it works on the Discord server. So please go and participate. And you can get on the voice stream channel like Tony Lambrex does, and somebody called EJ is also there. And you can ask questions directly. If they would just say something, they would be on the stream. So let's see. Pyro. R6 has had me occupied. Weird that my PC, not logged into YouTube, knows about this stream before my phone. Last time I got a notification with the same prominence like some important personal message. Yeah, you can't depend on YouTube's notification system to be told of anything. I I lament that system quite a bit, because it's pretty messed up. Nobody gets the same experience. It's like Facebook, right? They just show you whatever's misinformation they want to show you at the time. So there should be an invite in the description on YouTube, and on Twitch you should be seeing a Stream Elements timer with an invite on it as well. So that's different ways you can go. Okay. Oh, I see. You were talking about this being 1 hour old. The stream. Oh, yeah. That's so you're talking about you were. Yeah, I get what you're saying. Yeah, SOHO, Solar Heliospheric Observatory. Let's just go there one last time. Let me just let's just see what. Let's see. Is it SOHO Helio? I'll just do it this way. They have us. I used to know the URL, but I don't know it anymore. There it is. Yeah, SOHO www. It's very old. This website. This spacecraft has been up in the L1 point since 1995, folks. It has been up there taking data in a variety of wavelengths. And here is its you get a little measure of the solar wind. Here are its wavelengths. Here are the C2 chronographs, or the LASCO chronographs. And let's see, SOHO real-time view of the sun. They look at the sun in, I believe it's ultraviolet, and I forget what EIT is. Well, anyway, here's LASCO C2, and there's the limb of the sun, and it just so happens that this area in here that is blank, that is the area for Mauna Loa. So you can put in the K coronagraph image in there, and it will dovetail nicely with the LASCO C2, which goes out to this many solar radii. So what is that about? That's about a 1 solar radii or 2 solar radii. So that's LASCO C2. And then there's LASCO C3, which goes out even further. There's the limb of the sun. There's the pylon that holds the chronograph in place, or the Leo filter. And then there's the outer corona right here. So you get you can get 3 different viewpoints of the solar corona from all this data, and you can put together a movie if you wanted to gather all this up. But this is from today, just about an hour ago. And a lot of people have been using C2 C2 movies, or C3 movies, I'm sorry, to discover comets, because you can see comets flying through there as well. And here's an example of what I'm talking about. And here's 2 comets. Let me see here. Can I show this? No. Come on, man, just show it. QuickTime. It'll do QuickTime. Oh. All right. Well, you got to download it and then play it, and then you can see stuff. This is very Web 1.0, folks, so don't get too frustrated with it. But there's another resource for you. So what is that? 5 resources I've pointed you to. So please go make use of them. All right. Any last minute questions? I'm heading out. This is Ugly Hood Rat. Tony, if we found the planet with an alien civilization, and they were humans, would that prove the argument of a single creator? What is the mathematical probability of humans on another planet? Okay, well, that second part, I would have to say, is astronomically small, because the sequence of events that led to us here on Earth are very specific to Earth. So if we're going to find human beings that are very similar to us, and by similar, I mean maybe has 2 arms, 2 legs, and walks upright, maybe nothing else, breathes air, that's pretty damn remarkable. Now, as to whether or not that's a good argument for a creator, I don't think so, because, oh, I see what you mean. So it would be creating in his own image kind of thing, right? So because humans were created in the image of God, then if we found other aliens, that would fall in line with that argument, that all aliens everywhere, all intelligent life everywhere looks like humans, because that's the image of God. I suppose you could make that argument, but that's not a scientific statement, and you can maybe hang your hat on that if you're religious. But to someone who follows, to a scientific minded person, all that's going to be is an incredibly unlikely occurrence, and it would be a remarkable thing to see. And I would argue would say a lot about the ubiquity of intelligence in the universe. If that happened twice on 2 completely independent ways, then there's intelligence everywhere. Every single place you look would have intelligence, because if that happened, we just find one other place that's that close to us, I think we're going to find the universe teeming with intelligence. I find that unlikely, but I think that's what you could conclude from that observation. And as far as the creator thing, I don't think science has a lot to say about it. It's not a scientific question anyway. It would, I suppose, support your thesis, but it wouldn't be proof of it. So I think to see proof of a creator, we're going to need to see some pretty remarkable evidence, right? At least from a scientific perspective, something provable, something that is based on evidence. And I complain about things like string theory and quantum mechanics all the time because some of these things are just not provable. They will never be able to show us any evidence. So I am actually of an opinion that some of this stuff isn't science. They can't be backed up by anything observable or measurable or even that makes any hope of sense. So you may as well call it a religious thing. In terms of how much good it's going to do us. So I would say with that, from that perspective, it's not going to do much to prove your point. It might give you another thing you could say that would say, plus this happened in another spot. But what that really is saying, or what it really speaks to, is how ubiquitous intelligence would be in the universe. If we saw two planets with human beings on both of them, ours and some distant stars, wow. And they got there independently of anything we've done, no panspermia thing. Wow, that would be remarkable. Pyro. So people still believe Fermi paradox was a thing. Are we destined to destroy ourselves? Planet. Also, time alignment. Time and alignment. I don't understand. I understand some of what you're saying.
I think he's talking about how long our civilization exists. Like right now, we have what, a couple hundred of years of technocracy or whatever, or you can stretch it back to a
I would
couple
give it more
thousand.
credit.
Yeah,
I would go back to the Egyptians at least. Even Sumerians.
yeah,
Yeah.
but that's still a very short period of time so far. And I mean, possibly we have another billion years or what. Uh, I mean, it depends on how long intelligence actually exists. And so far, we've got what, a couple thousand years, maybe a couple 100,000 years if you really want to
Sure.
push it.
So in the window we've been around, there's civilizations could have come and gone. They could still be starting up later on, and we'd never know about it. Yeah. Of course,
Yeah.
and to go on with Fermi paradox, of course, it's a thing. It's a big thing to me. It's not a paradox. It's just where the hell is everybody? And I happen to think that it's entirely reasonable to say that we could be the only one in this galaxy, and there could be others like us, but we would never know that. And
depends on how long we exist for. And I mean, right now we have a potential
and
for.
that's the timing part, right? Sure.
Yeah.
Yeah.
But what we have right now is pretty small sample size.
Yeah. Raj wants to know, when I say never, do I mean because of current technology and observations, or never ever when it comes to string? Oh, ever. I mean, we're talking about strings that are less than the Planck length. Now, unless our basis for physics is wrong, nothing can be smaller than a length than a Planck length, which is like 10 to the minus 32, something super ridiculously small meters, right? So and this comes out of the Heisenberg principle, among other things, and I think quantum theory to a lesser extent. That is the smallest thing we can ever measure, period. Is something that is a Planck length long. And the second, we can never measure anything faster than a Planck second, right? These are fundamental limits beyond which we cannot go according to what we currently have for a physical framework. Now, that's not going to say there's not some more physics that can come along later and say, yeah, it turns out that you can actually see things shorter than the Planck length. These strings are so tiny that they make a Planck length look big. So I don't get how we're ever. So no, we don't have any hope of seeing these. Same with their dimensions that they talk about within 11, or it's either 11 or 500 dimensions. It depends on who you talk to. This cosmic landscape stuff
Yeah.
is just words and math.
Yeah.
Now, the only way they're real is if you happen to be like Plato and you think that Plato or that math is reality. That math just isn't a language that describes reality. It is real if it's mathematical. That's what Plato believed. And if you're of that nature, then okay, then these models and this math can reflect reality, and it is reality. We can't interact with it ourselves, but math can.
I think it comes down to that one of the first principles of science is observation. And when you get into string theory, there's no method that we are aware of making an observation.
Yeah.
So how can it be real? And I mean, I understand that Plato philosophy, but I mean, science is built on observation, right? It's what we can measure, what we can put into tangibility to ourselves, and if it's not observable, it gets really sketchy.
Right.
Right.
Exactly. So what do we do with that? What's science supposed to do with that? Well, I mean, you can do the math, but all math, we can write math to do a lot of things. Some of it real, some of it not. Uh, and so, what are we then left to do? Do we call it truth? Do we say it reflects reality, or do we wait for some observations to come along? And I think science would say that you need to get some evidence behind you.
Yeah, and that's that fine line. I mean, you can. I mean, does the square root of -1 work? Yes, it does, and it does explain our observations, so we're accepting of it, right?
Yeah,
But
yeah, and I mean, and the math is right. The math is good. It's just that's as far as it goes, and it's mathematics, but is it science? I'm not qualified to say, but my gut feeling is no.
I think it approaches more hard science when you talk about being able to actually observe that and say, this is because the math works and this is what it shows, right? And we can see it in nature.
Yeah.
Right. That's what I mean. Einstein didn't come up with his theory of relativity in a vacuum. He was saying, "Hey, I'm seeing that the speed of light is constant everywhere," and that's what he. I mean, he built. Okay, how is this consistent, and what does that? So
and he
it's
also built
based
on
on
the work of
observation.
others that were already doing similar work, so he built on that as well. So you're right; he didn't come up with it by himself.
Yeah,
if he hadn't come up with
I
it,
mean,
others around him would have.
yeah, and that we can. I mean, like I don't have to come up with that theory myself. I can see that it makes sense, and I can see where there's something observable that will demonstrate that, right?
Right, and that's the
Like,
difference.
and
You've hit on it right there. It predicted something observable at some point. During this period in history, in the early 21st or the early 20th century, the first proof they could get their hands on was the orbit of Mercury. Right? They said if relativity is right, if space-time is really being bent by things with mass, then the sun should bend the space-time around it, and if it does that, then it should bend the light that's reflected off of Mercury at us in such an angle that we would see it here instead of there. And of course, because it's so close to the sun and it's so bright, the only way to really see that light, reflected light from Mercury, is during an eclipse. So they waited for a lunar eclipse and they went out and they said, okay, if I'm right, then you're going to see that Mercury is over here and not where Newton said it would be. And sure enough, it was exactly where it should have been. With relativity predicting it. Boom, big feather in the cap right there for relativity theory. And then of course, ever since it's just been, backed up over and over again with
yeah,
observations
yeah,
as technology
yeah,
got better. But here we're going to be reaching limits where technology can't
that we
help
have.
us. No, no,
Or that we
these are
don't have. I
fundamental
mean, that's the thing, right? We
or
don't
will
have the
ever
technology
have
or even a way of
or
figuring it out.
or will ever have. These are fundamental limits to the universe that prevent us from making any instrument that can see things down to the level of these strings. So you cannot make an observation about strings ever. There is no predicted observation to make. And so that's where it falls way short of being science.
yeah, it gets into to the point where, well, you can't see it, so how can you prove that it doesn't exist? How can you prove that it does? Because you can't see it.
Yeah, well, right.
Yeah, it's I mean, and you build your foundations, right? I mean, because we don't see the spectrograph directly, but how do we know what we know, right?
Yeah.
And you can understand the basis of it. It's not something that, but that foundation is on observation. How can we see this, right?
Yeah.
And when we see it in the spectrograph, well, yeah, that's and we understand the previous observations that we did to get to that point, right?
Hmm.
And that's not something that you see with string theory.
Yeah.
And so I 100% support you. It gets
Yeah.
into
That's why
yep.
Michio Kaku is such a jerk. He's a string theorist who's trying to be relevant. He just can't be. Okay, Nikita Net on Twitch. One could say God is cruel if there's others out there. We know about them and we're never able to touch them because of the speed of light limits. Yes, it would be cruel, wouldn't it? And Abdul is commenting, I cannot believe there might be alien life right now in this moment in the ocean of Europa. That would be a big deal on so many levels. But the biggest deal would be towards an argument of there being life, that life is common. A real critical question of any life that we find on Europa would be, is it there because of something that came from Earth? In other words, traveled from Earth and seeded life there? Or did it start on Europa all by itself in parallel with life starting here on Earth? If it's that situation, one solar system, two planets with life that evolves separately on each one, then you've got a great argument for saying that life is common in the universe because it happened here in one solar system twice independently. That would be amazing to say that, that would be a good argument for, and in fact, I would be the one shouting it at the rooftops. Life is everywhere. Life is everywhere. Woo! Life is everywhere because it would be true. That would be it would make life very common. And that answering that one question would be such a huge step in humanity. I think for a lot of reasons, but not the least of which is it help us appreciate our own place in this universe more. And I don't know. I on the one hand, well, we were going to Europa with Europa Clipper. We're going to fly around it and look for some good spots to land, and then of course the Europa lander mission will land there, but that's not being built yet. Just the Clipper mission is being built right now. So, yeah, it would be. It's an amazing thing. Um, Let's see, a couple more comments, and I got to go. Fermi paradox. I would say this is from Pavel. I would say that if they were not destroyed, they created universe with better conditions for themselves. That's true. I guess so. And then Pyro comes in. Humanity will destroy itself. You sound like me. I say shit like that all the time. If this is a template, plus if our window and their window was this short, what was their probability of that either one of us would see the other? Yeah. I know it's already I get your timing thing, right? I get that. And that's a big deal. I mean, that's kind of an argument for there being life that is common though, because what you're saying is that civilizations can come and go, like bright sparks in the history of the universe and die out, but they won't spark at the same time and see each other. That would be too many things that have to come together at once. And but it still would imply anyway that that life in the universe is pretty common if we have these civilizations popping up throughout the history of the galaxy. Let's see. Galaxia's comment. Hi, Galaxio. I agree that we could be the only one, or there would be one civilization like the Greeks right now at the opposite side of the Milky Way, assuming humans would happen again at the same time in the Milky Way. Yes. Yeah. So there could just be one at a time, and that's kind of what Pyro's arguing. That there's one here, and it lives and dies and kills itself, and then another one pops up somewhere else. That could happen, and we'd never know. I think some would argue that, well, gosh, if some civilizations can get to a certain point in their development, then we should be able to see evidence of that in our observations. Some technosignatures that are out there, people are looking for those. But others of those, like me, who happen to think there's great filters to dodge all the way through the life in the universe, then I happen to think that great filters would be would be ultimate stopping point for a lot of these civilizations. I happen to think technology ends up being one of the great filters. I think we get to a point where we develop technology that we can't handle, and it ends up killing us, or we end up just acting like viruses and consuming all the raw materials in our area and dying out for lack of anything else to eat. So that's another bias I have, just because I have almost no faith in human beings.
You have no faith in humanity.
I don't. I am so discouraged right now.
And I question it, because we're basically animals, right? And that are capable of intelligence. But there's times where I know myself that I'm not that much farther from an ape than
the more advanced we get technologically, the more of a knife edge we sit on, the less there is room for error. Back in the dark ages, you could hate another country, you could conquer another country, you could eat all the natural resources in your area and still be fine, just because you weren't big enough or technological enough to do much damage. Yeah. Nowadays, the error bars are much, much smaller. We can't screw it up too much. If we get really mad at China and decide we're going to blow it up, we got some ways to blow it up, and they have ways of blowing us up. So the chance for failure goes way up, and not even get started on artificial intelligence yet. So we need to be careful going forward as we get more of these tools. They're going to make us more powerful. Yes, they're going to make us more able to see into the future, into the universe, and understand the universe better, make us smarter. But they also have less room for error. And human nature does not give me a lot of hope, because I don't know that we can mature, gain the wisdom required.
Intelligence is a survival mechanism, if you ask me. Okay, it is what has allowed us to get to the point where we are. Now, I'm not saying that we're I think that the real issue that I have is that we're evolved to be capable of intelligence. It's not that we are ruled by intelligence. And the deal is we have a limited lifespan, we have limited resources, and if we do not become a multi-planet system in the first place, then when the sun gets too hot, we're done for anyways.
Yeah, I don't see us lasting anywhere near that long. But you're right. I mean, we got to get a handle on this before it gets a handle on us, and that's where I am pessimistic. But I don't want to bring people down, so I won't go into it. I won't go into it too much. Let me just get a couple more. Boy, you guys are doing some good questions. Would you want humans to interact with alien civilizations that was in their medieval era? Well, would I want them to? Sure, man. Why not? Just knowing they're there would be huge. And if they're in a medieval time, what difference does that make? I think we should definitely interact with them. It'd blow their minds, but I don't know how we would. I mean, the distances to these stars are so great that even they're not going to have any ability to listen to us if we send a signal. So I don't know how we would do it in that way. Yeah, and of course that's always the question, Pyro. Is intelligence life? Is intelligent life? How did it happen? That is right. Are we a fluke? How rare is it? I happen to think intelligence is more rare than life. So that's another reason I think that of all the billions of stars, this is it. We might be it. Okay, I think I'm going to have to go, folks. I got to go. You know what? That storm came through and nothing happened. No lightning, no tornadoes, nothing. Panthers sound asleep on the floor. That turned out to be a big nothing. I was on tornado watches and everything. A little bit disappointed. I live in a hurricane zone. I'm prepared for this stuff. I want to see it happen. I want to see how my I'm a real prepper to see how it's working. Okay.
Yeah. La Palma has a live stream. The island wouldn't exist there if it wasn't for the volcano, but the volcano.
Pyro, nobody's suppressing any comments. If you don't see it, I don't know what happened to it. So, well, you're not being suppressed. I don't know what you mean. Maybe I didn't see it. So don't get mad. All right, this is from Canuck on Twitch, I believe. I would be extremely concerned with landing craft on Europa, whether or not there is life there. I would be extremely concerned for hitchhikers like tardigrades surviving the trip and contaminating the oceans with Earth life. Yeah, that's a real problem. It's the same problem with Mars, isn't it? So, I mean, they've got that system, I think, pretty well worked out as far as keeping things sterile. But you're right; it's always a risk. Yeah. Let's see. Let's see what I'll leave with Abdul's question or comment. Any life in Europa would be a completely new genesis, new form of life that has different DNA or whatever thing that they use to store bioinformation. Well, okay, that's a statement, but we don't know yet. We would need to find out if there is life. You can be sure there's going to be a lot of effort put into the question of, did it start here first? That's the first thing we're going to want to know if we find any there. Okay, we found it here. Woohoo! Where'd it come from? Did it come from here? If it came from here, then we'll be able to tell by a lot of little biosignatures that are from life here. Probably find some similarities to life here on Earth. It could also be inconclusive, which would really suck. All right, we don't know. It could also be from somewhere else. Now, what you're talking about is a completely different thing. If that happened in parallel to life evolving here, then my statement still stands that I said before. That shows that life is pretty common in the universe, because not only did life happen twice in the same solar system, it happened in two completely different ways using something else besides DNA. So that's going to be even more remarkable and less likely. So less likely, but amazing. So a lot of things to find out. So, okay, guys, I've got to go because I went really longer than I wanted to, or than I should have. I definitely enjoy spending time with you guys. So that is it for this stream, guys. I will be back next week, where I'm still working out the schedule of some things I'm going to talking about. I think it was Pyro. I think you were the one who posted the question last week that Tony helped me understand about black holes forming without supernovae. I think that was you that asked that last time. I want to do a whole stream on that. So I'm doing my research on that coming up, and I'll do a talk on it. Don't know if I'll get to it next week, but that was inspired by you, because that was a good question. I found myself thinking about it after I understood it, because I wasn't reading your comment very well. But that turns out to be a good question. So I wanted to know more. So I will stream about that either next week or the week after. That's on my list here of future streams. So thanks for the idea. If you guys have ideas for streams you would like to see, please leave them in the comments or go on Discord. You can PM me anytime you want on both Twitter and Facebook, and well, not Facebook so much. I'm never on that, but YouTube and LinkedIn, even if you want to do that. It's all the same. I'm same handle. Don't do Instagram much. Anything Facebook's related, I don't know. I just kind of stay away from that. So, but I'll probably get an alert if you send me a DM on those. Okay,
come on over to Discord.
Yeah, definitely do that. Do that. You just go on Discord. That's where I've always got this window up. You see this? Here's my desktop. So here is there it is. That's Discord's always up in this window right here. It's always on my desk, and I'm ready to go. Okay. That's it for this stream, space fans. Thank you so much for watching, and I will talk to you guys next week. And as always, keep looking up.